Hello IGCSEers, we're learning about pressure. It's quite a nice sort of fairly simple. We're just going to think about pressure and then we're going to introduce an equation and then we're going to play with the equation a bit. So I'm going to use this lesson as an opportunity to revise a couple of things as well. Just a little bit about forces. If you have not yet seen the forces and motion module that I taught, don't worry about it. When you get to the forces and motion module, you'll be like, oh yeah, this makes more sense because of that lesson on pressure that we did. So the first thing I want you to do, please, is to get a fair amount of Play-Doh and roll out 2 flat discs for me. So split however much Play-Doh you've got in half, roll it into 2 balls, and then push it into 2 kind of disc shapes. What we're going to do is, you should have a full can of food with you. We're going to drop the can of food onto both of the discs. So you just need 2 Play-Doh discs that are obviously big enough that the can land on them. They don't need to be very thick though. Right, there's one. Yeah, I don't want to tell you too much about pressure. Some of you will know about pressure already. But I just want to do this activity first to get you thinking about it, because I was getting some really good, incredibly thoughtful answers on Facebook yesterday. And my physics teacher was really good at asking questions. They would just bring something really simple in and ask you a question like, what's going to happen? And then you'd think, oh yeah, I know. But then as you started to answer, you'd realise that actually you didn't really know. And every answer you gave, my physics teacher would be like, yeah, but why? Yeah, but why though? And in the end, you realise you didn't have a clue. So I'm hoping that we'll get some kind of reaction like that from you today. So here we go. I've got my 2 little Play-Doh discs. And we're going to drop a can of food onto both of them. But we're going to do it, the first time we do it, we're just going to hold the can upright and drop it. And the second time we do it, we're going to hold the can upside down and drop it. All right? So we'll drop it the right way around onto one of the discs and upside down onto the other one of the discs. In order to be fair, we're just going to observe what happens to it after that. But to be fair, really, we'll have to drop it from the same height. I'm just going to measure with my fist. I think I'll put my fist on the ground and I'll drop it so that it's level with my fist both times. Yeah, I reckon that'll be okay. All right, come down here with me. I am ready. Oops, that is my kitchen and Lego story time. There we go, that's better. Not Lego story time show for if you happen to be new. I'm not telling you a Lego story today, but I do that as well in other shows, which you are welcome to come to. They are also free. Right, here we go. So the first one, so I'm going to put my fist there, and I'm just dropping a can of beans from the height of my fist onto a Play-Doh disc. There we go. That was easy, wasn't it? I'm going to do it again. You don't have to get it kind of exactly matched up each time. There we go. Observe. Ooh, results. Now I'm going to do the same thing, but this time I'm going to do the can upside down, right? Behold. Same height to make it fair, so that I know the difference is to do with the difference in the cans. And repeating my experiment as well, right? Because that makes it fairer as well, so that you know that your result is what's generally going to happen and not just a one-off. I'll just repeat the first one again, right way up. Okay, what are you seeing? And why? What are you seeing? And also why? So this is the first one. We've got some marks. And this is the second one. It's sliced into it. In some places, it's nearly cut all the way through the Play-Doh. Why? What is the difference? Well, let's have a look at our can. So the bottom of our can is quite rounded, right? It's quite, I suppose you could say blunt. And the top of the can, what are you going to say? You could say it's quite sharp. It's quite thin. It's got this very thin ridge around it. Why, when you drop the blunt end of a can from the same height onto the bit of Play-Doh, does it dent it, but just put a little dent in? And when you turn it upside down, it slices in much deeper, right? Can you see it's gone further in? Why is that? Why? But why? So on Facebook yesterday, what were they saying? People started immediately talking about, actually what they started talking about was something called surface area. you might be thinking about surface area, so I'll write that on the board. What do we mean by surface area? We mean basically like all the area that's kind of on the outside. So the surface area of the can would be every single bit of this can that was sort of on the outside, right? On the surface. So let's not talk about surface area, because I don't think that's really what the people on Facebook meant. I think they meant the surface area of just the top of the can, just the bit of the can that was touching the Play-Doh, all right? So they really meant the area of the can that was touching the Play-Doh. So we'll just say area. Why does the amount of area make a difference to how much the can was cutting into the Play-Doh? Let's talk about surface area, about area a bit more. So this is let's say this is like the blunt bit of the can. Are you okay with the fact that if this is the Play-Doh here, I can do it purple, then quite a lot of the surface of the can, when we first did it, was touching the surface of the Play-Doh. Whereas the second time, people were starting to talk about like sharpness and pointiness on Facebook. The second time, the ridge of the can it's sharper, right? It's more pointy. So less area was less area was in contact with the Play-Doh. Is that okay? I think that is definitely true. What else can you talk about? Some people were talking about force. Maybe you've been thinking about force. You would be correct, right? In other lessons, we've talked about how weight is a force that's sort of pulling everything down. The can definitely has weight. It was the same weight in both activities, wasn't it? It was the same weight both times, so and the same height. So the can was hitting the Play-Doh with the same amount of force each time. But you might be thinking about force. I think I need to get myself some new whiteboard pens for Christmas. I will. Have I been writing backwards? I hope not. On Facebook I have to write backwards. I'm now starting to second guess. Anyway, that's written forwards. Force and area. If you've thought about force and area, well done. That is what we're going to be thinking about today. They are very related to pressure. The first time we did it, the blunt end of the can didn't put as much pressure on the piece of Play-Doh. The second time we did it, it's a very, very small area, that put a lot more pressure on the Play-Doh, so it cut through. If you've got a pen or a pencil with you, which I blooming well hope you have, then you see the same sort of thing with that. Like it's got a sharp end and a blunt end, right? The sharp end, if you touch that against your finger, if you just push it gently against your finger, you can feel that has the potential to cause you quite a lot of pain, right? Very, very small area, touching, being pushed against your finger, that's quite a lot of pressure. If you turn it around, you can push with exactly the same amount of force, but now there's a larger amount of area in contact with your skin. It doesn't quite feel as risky. So why is this? Well, first of all, I'm just going to give you the sheet. I'm going to give you this sheet of questions. I've got some examples of situations where a high pressure, for example, a little tip of a pen pointing to your finger, that would be high pressure, a lot of pressure. Examples of when that's useful, and examples of when low pressure, so something with a bigger surface area, when that would be useful, and some of them are both and some of them are neither, just to try and confuse you, because with confusion comes learning, or something, probably. Here we go. So just to remind you, if something's got a large area, that generally means low pressure or lower pressure. And if something's got a small area, that means that there is some high pressure happening. So which of these examples show low pressure being useful, which show high pressure being useful, which show both, and which show neither? So for example, a bulldozer's caterpillar wheels. Bulldozer doesn't have wheels, it's got these big, wide, very large area tracks hooked over its wheels. Is that an example of low pressure being useful, or high pressure being useful, or neither, or both? A shark's teeth. Shark has very pointy teeth. Is that an example of high pressure being useful, low pressure being useful, or neither, or both? I'm going to try and use my Play-Doh lid to get you a bit higher. Yeah. So pro. A woodpecker's beak. Is that high pressure, low pressure, neither, both? Is it useful? The base of a high chair being wide. Is that related to pressure? If it is it high pressure or low pressure? Is that useful? Snowshoes, a bit of a small picture, sorry. Hopefully you know, the snowshoes are kind of tennis racket type shoes that attach to people's feet to make them be able to walk in the snow. Ice skates. an umbrella, and a drawing pin. Are they examples of high pressure being useful, low pressure being useful, or both, or neither? If you finish, can you start thinking about the equation for pressure, please? I've given you force and surface area as a massive clue. What's the equation for pressure? I'll write it on the board just while you're finishing off. Ten seconds, and then I'll go through it. All right, a bulldozer's caterpillar wheels then. Well, yeah, that's a large area. So that is definitely a situation where low pressure is useful, right? Very, very similar to our Play-Doh activity. If it's got a larger area, it's putting less pressure on the ground underneath it, so it's less likely to, say, sink into the mud or whatever kind of difficult ground it's crawling along on. A shark's teeth, that's the opposite, right? Shark's teeth have a very, very small area, so that they put a very high pressure on the things that they want to bite. And the same with a woodpecker's beak as well. So it's very, very small, sharp, pointy beak, so that with a reasonably small amount of force, you get high pressure, so it can hammer into the tree. The base of a high chair is very wide. That doesn't have anything to do with pressure. That design is not related to pressure at all. I was going to show you why. Shall I show you why? I'll just do a real quick little side revision lesson on why the base of a high chair being wide doesn't have anything to do with it. Because it's actually much better for your brain to keep remembering stuff as you go along than it is to do one big bit of revision at the end. So it doesn't matter if you've never heard of this before in your life. The design of a high chair is related to stability. So we did this in our forces and motion lesson when we did about centre of mass. The centre of mass is kind of a point on a thing where you can imagine that all its mass is concentrated. So let's say the centre of the mass of this bus is just above the steering wheel. You can draw this imaginary line from the centre of mass to the ground, and that's called the line of action. And the rule for stuff being stable is when you draw that imaginary line, the line of action, down from the centre of mass to the ground, if it's within the base, then the thing isn't going to fall over. So here the base is just between the wheels. So here the bus has tipped over, but this line of action from the centre of mass to the ground, it's still just within the wheels. So this bus isn't going to tip over. If you make the centre of mass, obviously I've put the situation not ideal, do not try that at home. If we make the centre of mass a bit higher on this first bus, and then draw our line of action again, then you can see a higher centre of mass makes things less stable, because now the same bus, the same angle, but with a higher centre of mass, say if loads and loads of people were sat on the top deck and no one was on the bottom deck, then that line of action falls beyond the base, and that bus is going to tip over, right? So a high chair, I've put here, it's the base is wide, so that even if a baby pulls some 100% baby nonsense and tips the high chair really far over, the centre of mass might move to the edge, but it won't go beyond the base because the base is super wide, right? So it's not about pressure. Like if we're looking at pressure, the area of the legs is very small. This one in this picture is really pointy, but the baby's weight is quite small. So like small area, small force, pressure on the floor is going to be fairly low. Plus, like, just not worried about that when it comes to baby safety. Okay, moving on. Snowshoes, yeah, large area. So again, low pressure, same as a bulldozer, so that you don't sink into the snow. Ice skates, that's actually neither. The design is not related to pressure. Did not know this before I researched this lesson. Here's a lovely, beautiful big ice skate. Oh no, it's gone. Oh, I hate it when that happens. There we go. So obviously the area of an ice skate is extremely small. So there is a lot of pressure on the ice, but that is to reduce friction so the skater can move around. It's not an example of pressure being useful. This was a good lesson in read the question. It has got a small area, so it has got high pressure, but I asked you for if it was useful or not, and it's not. Some people saying on Facebook yesterday, you've read the internet carefully. Some people saying that the pressure on the ice is what melts the ice. Apparently that's not true. I didn't know this. There's a myth that pushing down on ice with an ice skate melts it, and that's what allows there to be like no friction. That's not true. An ice skater does skate on a layer of water, but we're not sure where that water comes from. It might be that it's pushing water particles. It doesn't matter. It's not about pressure. An umbrella is also not about pressure. Did you get that? It's got a very big surface area, but that is to catch a lot of rain. You're not worried about really spreading out the force of the raindrops on the umbrella. And a drawing pin is both. Drawing pins have a pointy end, so very small area, which means that if you're pushing it into the wall, there's a lot of pressure on the wall, so it goes into the wall. But the other end has a large area, so that if you apply a lot of force to get the pin into the wall, you have a low pressure on your finger, so the pin doesn't go into your finger. Humans with their inventions. Brilliant. Right. Did you put together some sort of idea as to what the equation for pressure is? Here it is. Pressure equals force divided by area. Well done if you got that. I feel like I keep saying surface area. Do not say surface area. It's just area. So for example, when we were doing our can activity, and we had the Play-Doh here, we weren't worried about the whole surface area of the can. We just wanted the area that was in contact with the Play-Doh, right? So it's the bit that's in contact with the thing. So yeah, pressure equals force divided by area. Yeah, hopefully that's fairly easy to understand, because it's just how much the force is spread out over an area, right? You're sharing the force out over a certain amount of area. If you share a large force out over a small area, then pressure is going to be big. If there's loads of area, then the pressure is lower. Is that all right? The thing to be really careful with here is that last week we were looking at density, and we were talking about how density is mass per volume, and I was saying, you can, as long as your units are the same on both sides, you can kind of do whatever you like. So you could say that density is measured in the amount of grams per cubic centimetre, or you could say that density is the amount of kilograms per cubic metre. Pressure, you've got to be super careful, because there is a special unit for pressure. It's the Pascal, named after Mr. Pascal, so you write PA, is the unit of pressure. And that Pascal is newtons per metre squared. That's what that means. So you can't just take an area in centimetres and do the equation and then give your answer in pascals, because then you'd be using centimetres squared. Because then you'd be using centimetres squared on one side of the equation and metres squared on the other. That's not going to work. So always, just before I give you your question sheet, like in a second, always, if you're using the pressure equation, convert your area into metres squared. Make sure your area is in metres squared, because then when you use pascals, that'll be right, because you'll mean newtons per metre squared. Is that all right? Don't be just plugging an area of centimetres squared or inches squared into this equation. Okay, I think you got everything you need. As long as you can rearrange basic equations, you can have a go at this sheet for me. Yeah. See, I have to release the worksheets and then I teach the lesson. And in the lesson, everyone points out the obvious mistake in the worksheets, but it's too late for me to change the worksheet. Question number 6, I've asked you about an ice skater. Can you imagine that the ice skater has both feet on the ground? I know, that's not really how ice skating works, is it? Just imagine that the ice skater has both feet on the ground, okay? And then all will be well. Here we go. So, questions. A force of 40 newtons acts over 5 metres squared. What is the pressure? Here's your equation. Pressure in pascals, PA, equals force measured in newtons divided by area, which is measured in metres squared. So if your force is 40 newtons and the area is 5 metres squared, what is the pressure? A force of 30 newtons exerts 10 pascals of pressure. What area is it acting over? Just rearrange it. Right? A 2 metre square table feels a pressure of 16 pascals. How much force is pushing down on the table? A truck weighs 400,000 newtons. The surface area of each tyre is 1 metre squared. The truck has 6 wheels. If you're watching live, then your worksheet doesn't tell you how many wheels. It's got 6 wheels, okay? So how much pressure does the truck exert on the ground? If it's got 6 wheels and each wheel, the area touching the ground is 1 metre square. Question 5. A shoe has an area of 0.05 metres squared. It exerts 800 pascals of pressure on the ground. What is the weight of the owner, who is pictured in newtons? What is the weight of the owner in newtons if they exert 800 pascals of pressure on the ground? They've got both feet on the ground. And one shoe has got an area of 0.05 metres squared. And finally, an ice skate is 0.5 centimetres wide and 30 centimetres long. A skater weighs 850 newtons. How much pressure do they exert on the ice if they are skating with both feet on the ground? If they're skating with both feet on the ice? That's nice, a couple more people have just joined live. The whole lesson hasn't been staring at this sheet, but we are doing that for like another minute now. And I'm trying not to sing under pressure out loud, only in my head. How are you getting on? Should I give you 20 more seconds? Don't forget that the ice skater has got both feet on the ground. Also, this person weighs a sort of surprisingly small amount. We are going to say that it's a child. Not that I made a mistake, that it's a child. Very, very small child. All right, let's go through it then. So a force of 40 newtons acts over a pressure of 5 metres squared. There are no trick questions here. You just plug that into the equation. So it's 40 newtons divided by 5 metres squared, which is 8 pascals, right? 8 PA. You have to do a little bit of rearranging here. If the force is 30 newtons and the pressure is 10 pascals, then you had to rearrange that and know that area equals force divided by pressure. So then you just do 30 newtons divided by 10 pascals, which is 3 metres squared. Well done if you got that. A 2 metre squared table. feels a pressure of 16 pascals. So again, you've got to rearrange the equation for force this time. However, I don't want to teach you how to rearrange equations because everyone's got their own way of doing it. Force equals pressure times area. So it would be 16 pascals times 2 meters squared, which is 32 newtons. At this point, I would like to highlight the fact that you should all have definitely written newtons. I hope that you didn't just get a bit cocky and be breezing through it and think, oh, well, I know it's newtons. No, you need to get into good habits, please. If you're doing an exam question and there's loads of different stages, you've got to keep track of what you're working with. So if you can see that your answer's 32 newtons and it turns out you were trying to work out a force, that's a good sign that you're doing things right. So give yourself 2 marks if you put newtons there. A truck weighs 400,000 newtons. The surface area of each tyre is 1 metre squared, but the truck's got 6 wheels. So before you work out the pressure, you've got to work out the total area that is in contact with the ground, right? There are 6 wheels, so the total area is 1 metre squared times 6, which is 6 metres squared. And then you can plug that into the equation. So 400,000 newtons divided by 6 metres squared is, I made a mistake here, didn't I? I should have rounded that. It's actually 66,666.7 pascals. If you know about significant figures, you will have to know about them for your exam. If you don't, I'm not going to teach it all here. But just to say that this number, you don't know where this number's come from. This number could have been like 410,000 newtons and someone just rounded it down. So the only you really only can say you've got this number to one significant figure. So it would be okay to change that to having a one significant figure answer as well and make it 70,000 pascals. But don't worry if you didn't understand that, it's perfectly okay. If you've got 66,666.7 pascals, that's very good. Right. This shoe has an area of 0.05 metres squared. It exerts 800 pascals of pressure on the ground. What is the weight of its owner? Well, there's 2 shoes, right? So before we just start plugging into this equation, we need to know what the total area is. If there's 2 feet on the floor, then the total area is the area of 1 shoe times 2. So it's 0.1 metres squared for the area. And then you plug it into the equation, because I made a mistake. I was thinking about newtons and not pascals. You get 800 pascals times 0.1 metre squared, which is ludicrously small, 80 newtons. That doesn't make any sense. 80 kilograms is a reasonable mass. For an adult, 80 newtons is teeny tiny. It's a child, we'll just say. Well done if you've got 80 newtons. But what if this scenario, what if this tiny little child lifts 1 foot off the ground? Do they weigh the same? Just have a think about that. I mean, you probably know the answer, but why does the maths work? If this person lifts 1 foot off the ground, do they weigh the same? Have you done a little bit of brain exercise for me? Yes, obviously they do weigh the same. The area has halved, but something else has changed. It's not just the area on the ground that's halved. Obviously the force in this case is the weight, so the weight hasn't changed, but the pressure has doubled. Is that okay? Some of you, that might be a bit of brain gymnastics. It's like the same with the pencil. You can apply the same amount of force, but if it's a small area pushing against your finger, then you feel a high pressure. If it's a large area, you feel low pressure. So the force is the same, but if the area changes, then the pressure changes as well. So to show you that in maths, you can do it. If you double the pressure, 1,600 pascals times half the area, you will find if you put that into your calculator that you still get 80 newtons. Good. Physics isn't broken. Right. An ice skate is 0.5 centimetres wide and 30 centimetres long. A skater weighs 850 newtons. How much pressure do they exert on the ice if they've got both ice skates on the ice for reasons? You've got to convert the area into metres squared. Did you see this? You can't just use centimetres because Pascal means newtons per metre squared, and you've got to have the same on both sides. So let's convert our area. If it's basically a rectangle, 0.5 centimetres is 0.005 metres. Let's divide by 100 because there's 100 centimetres in a metre. And 30 centimetres is 0.3 metres. So we times that together to get the area, but what have I done wrong? Well, we've said that they've got both skates on the ice, so then you've got to double that. Is that okay? Work out, first of all, get rid of these centimetres and change them into metres, then work out the area, and then just double check that you've got the correct area, and we've doubled it, so that's fine. So then we get to plug it into the equation. 850 newtons divided by 0.003 metres squared, which is a tiny amount of metres squared, is 283,333.3 pascals. Yeah, I really didn't do that thing where you got nice round answers so you knew you got the right answer, did I? Not in the slightest. Right, I was then... In my lesson plan, and when I was teacher training, I was notorious for trying to cram too much into a lesson. I was then going to give you this whole big new question where we would do a little bit of revision about like the difference between mass and weight and how much people weigh on the moon and things like this. I'm not going to do that because I feel like you've worked very hard and this is a very good way to end the lesson. But I will put this back on the screen for a couple of seconds because I'd like you to try this for homework, please. If you've done forces of motion, it'll be excellent revision. If you haven't, actually all the information that you need is on the screen. You don't even have to go away and learn the difference between mass and weight if you don't want to, although it would be a fine idea, some interesting reading to do. But here you go. If you haven't got the worksheets from my Facebook group, maybe just take a screenshot of this, or obviously you can just come back to it. I've got you the footprint of my niece, who has a mass of 12 kilograms, and the footprint of my husband, who has a mass of 75 kilograms. I've given you their measurements, obviously. Oh, well, I haven't told you, but actually my niece is 2. So the footprint of my niece is much smaller than the footprint of my husband. Just assume that they're both rectangles, all right? You don't need to work out the whole area of the footprint. But I just want you to work out which one will cause me the most pain if they step on my feet. Which one is going to exert the most pressure on my foot? And as a little kind of extra bonus revision question, how much pressure would my husband apply to the ground if he walked on the moon? Assume a spacesuit weighs 50 kilograms, but we're not going to do that today. You can do that for homework, and then we'll go through it next week before we learn about thermal expansion. When stuff gets warm, it expands. It's just next lesson, but you don't need to come to next lesson now. I just told you it. Well done. You learned it. Right, I'm going to go to my Facebook group. Not my Facebook group, my Facebook page. And see if anyone has left me any comments. Oh, hello, Etienne's here. Oh, Etienne, I haven't seen your name for a while. How lovely. Oh, splendid. And Facebook has broken. Oh, hello, Samuel. Oh, nice to see you two here as well. Fabulous. Right. Have you noticed there's been no freezing? I mean, actually, there isn't usually on YouTube. I'm so happy with my new internet. Right. Yeah, that's the end of the lesson. If you want to support me, you totally can. That would be incredibly useful. There is no funding. The only way that this is my job, it's just ridiculously great, is that basically the kind of home ed community have just decided to pay me. All of you. You just club together every month. So I say £5 a month is enough. Hopefully that's a very reasonable amount of money for people to pay for the amount of work that I'm putting in, the amount of lessons that I'm providing. But also from enough of you, it's enough that I've got a teacher wage. It's such a good business model. So yeah, if you sign up to support me with £5 a month, you can do it by going to my About section on YouTube, and it takes you there. It's this website called Coffee. I will send you nice things even to say thank you. I do a big post out a few times a year where I send everyone Theatre Science magazine. Here it is. Everyone else I know now is saying Ko-Fi, but I'm going to keep calling it Coffee. If you search for Theatre of Science Coffee on the internet, then that'll bring you to it as well. Theatre of Science Coffee, support me with £5 a month. I send you some, I call them rainbow glasses, but actually you're IGCSE, so these are diffraction glasses. They make you see rainbows. They're totally amazing. I can't get over it. Oh, they're so good. I'll send you an information sheet that I wrote explaining how they work. And I'll send you Theatre Science magazine, like I say. You can sign up with £5 a month and you get the mould one, which comes with a compostable plastic bag. It did not cost me an insignificant amount of money, but I had to make it compostable because what you do is you make this little tray, you grow some mould in it, you identify the mould using the mould spotting guide, and then you compost the whole thing. So it's very good for the environment. Well, it's not bad for the environment. There's a choose your own adventure quiz that I wrote. You are a mould expert in a museum. Will you be fired or will you be promoted? It depends on the decisions that you make in the story. There's a beautiful comic that my husband illustrates for me about the discovery of penicillin. And yeah, these just like sometimes they're big, sometimes they're thinner, sometimes they're thicker. It depends. Like the longer they take me, obviously, the longer it is between magazines, but kind of the better they are when they arrive. This is the latest one. If you sign up with £6 a month, I'll send you this one as well. So it's all about weeds. It's all about those annoying little plants that people pull up or put weed killer on, and they're amazing. They're amazing. They had genuinely medicinal purposes that we utilised in ye olden times. It's got another beautiful comic. It's got a quiz. If you find a flower that looks a bit like a dandelion, it's not a dandelion. Work out what it is. I'm very proud of Theatre Science magazine. I'm working on the next one at the moment, which is on acids. So if you have signed up to support me, you are on my list and you will be getting that when it's ready. It's a little way off. Comic is finished, but I need to work on my "Which acid are you?" quiz. Someone's requested another choose your own adventure, but I don't know. They take a lot of time. They are the best though. Maybe we do need an acids choose your own adventure. Yeah, I'll have a think. Some more comments just before I go. Oh, Etienne found the maths hard. You're 10. What? Oh well, yeah. You probably did find the maths hard. Etienne, I do find the maths actually side of things really difficult, because when I was teaching in a classroom, just didn't have to think about it. Didn't have to think about it at all, because obviously, like all the kids in the class, they all went to the same maths lesson, so they'd all just learn the same maths at the same time, and I just knew that they knew it. Whereas these lessons, obviously some people come and they know all the maths and they're really comfortable with it, and some of them have only maybe just started doing maths. So yeah, like I worry that people will think that I expect you to know it, but it's not that. It's just that I've never taught it before and I'm a bit scared of teaching maths. I just don't know, just don't really know how to teach maths. You get taught how to teach stuff. I got taught how to teach science. Would the caterpillar tracks on the vehicle also have high pressure because they've got little grips on them to stop them slipping? Oh, that's such a good question. Wow, oh my goodness, that is so good. Isn't that brilliant? Yeah, I suppose you're right actually, because presumably those little grips, so Samuel's talking about, we've got the caterpillar wheels and we've got these tiny little bits on the caterpillar wheels. Yeah, you're right. Of course, they're designed to have a high pressure, aren't they? Because they're supposed to sink into the ground, because that's where the grippiness comes from. Yeah. And now I'm trying to think about like what makes it, because yeah, I guess enough pressure here that they, exactly. Yeah, I mean that's absolutely brilliant. Yeah, they've got high pressure so that they can sink in, so the whole thing doesn't slip. And I suppose like a bit more friction as well, actually, because if they're pushing in this direction, then friction will be pushing back, which we did in our previous forces lesson. But yeah, probably it's also important, isn't it, that they do sink into the ground? Yes. Glad I came back to the comments. Okay, you lot. Etienne, very well done for persevering with the maths. Yeah, if you find it hard, it might be just because you actually haven't learned it. So you just have to go to BBC Bite Size or something and look up how to rearrange equations and things like that. Okay, I'm going to go and tidy up because my desk is a total mess. So it's Lego story time tomorrow about chickens versus turkeys, if you're watching live and you want to be back on YouTube at 10:30 tomorrow. Otherwise, I'll see you next week for another IGCSE physics lesson. Bye!